Okay. So you have like two packets in front of you, right? So the one with all the text are your notes. Okay. It's basically going to be like a summary of the things that we'll cover. I will encourage you to take extra notes. So if I like draw a diagram, you'll see that diagrams are kind of like missing. There's no like visual things in there. So I recommend that you follow along and like draw your diagram in your notebook as we go along. And then the second package is the workbook. For this chapter, we have 26 questions. We'll go over roughly like a third to a half of them together in class because I like to go back and forth between the notes and the workbook. But the rest is for like, you know, homework, because we just practice between classes, okay? So, what was your last completed course again? FCalc 11? Yeah. And then PDP 10?
What, physics 10?
No, PDP. Have you done PDP?
No.
You're also FCalc 11?
No, I mean I was, yeah.
Like, what did you complete before?
Oh, FCalc 11.
FCalc 11. Yeah, I think a lot of people don't do PDP, and then they do just fine in IB. Yeah. Okay. So our first chapter now. Do you guys like know what calculus is about, like beforehand? Before we start? No, is this your first time? Yeah. Okay. So there's three main units. Okay. Three. I should better one. Topics. Calculus deals with three topics. The first one is limits and continuity. So that's the first unit that we're doing. This is going to be, I think this is going to be like the most unfamiliar, like sort of new thing that gets thrown at you right in the start of the calculus course. Every calculus course starts with the concept of limits and continuity. It's going to be a build-up for the second main unit, which is something called differentiation. And then, knowing units 1 and 2, the third major topic is integration. Okay? So we learn it in this order, right? Limits and continuity, differentiation, and integration. This is how we learn, but if you actually look at the history of the subject, it actually goes backwards. So historically, integration is sort of about finding the area of weird shapes. So we're all familiar with the function y equals x squared, right? Y equals x squared, yeah? And then what does this pass through? It passes through 1, 1, right? So integration asks the question, what's the area underneath this weird curve here? Because we've sketched a lot of, quadratic functions. But I guess people were interested not just with y equals x squared, but with like all sorts of like weird curves and shapes. How do we, get to finding the area that involves these curves? So that's the main idea of integration. I'll get more very specific when we actually get to the unit. Differentiation is if I have a tangent line at this point, what will that slope be? That's the main question that differentiation tries to answer. And the limits and continuity will be the building blocks of all of these tools. But ultimately, the main thing that we want to do in calculus is to analyze functions and their graphs. So all these new tools that we'll be learning helps us to deeper understand the functions that we know, right? By the end of this course, you're going to be very well informed on quadratic, cubic, and we'll be dealing with polynomial functions, so that's functions that has x to the power of n with it. In a full calculus course, after you guys study pre-calculus 12 or complete your first IB course, you'll be studying trig functions, exponential, logarithmic, all of that. But for this course, it's foundations, and we'll go very deep into polynomial functions. Because polynomial functions are kind of very easy to deal with. They're very easy to do these kinds of operations on. And as I said in the orientation, the main scope of this course is to really understand the core ideas of this and not necessarily to focus too much on the actual, the computations. The computations you'll get to learn in the full calculus course. Okay, so with that introduction, let's get started on our first chapter. I will bring better marker pens next time. Yeah, that's a thing to keep in mind. Will this one be better? Okay, so first unit, limits and continuity, and the first chapter is the limit of a function. Okay, what do we mean by a limit of a function? You guys are paying attention? Yep. Okay, cool. So our journey with calculus, guys, we start on the number line. Okay, so you've all seen the real number line before. Yeah? So it's very simple. Okay, I'm going to pick a point on the number line. I'm going to say that this is A. Okay, A can be any number that you want. But I want to pick this point A. And then look carefully at what I'm doing here. I'm going to pick another point on the number line, and then this point is on the left side of A, right? It's smaller than A by some amount. But what I'm going to do is I'm going to push this point, I'm going to move this point closer to A. You understand? Right? So I'm going to push this closer to A, move this closer to A. But the key idea here is that this point gets very, very, very close to A, but it does not actually equal A. That's the most important idea, okay? So while this point gets as close to A as you like, it's very, very close to A, it does not actually equal A, okay? And we call this action, okay, so this number line, let's say this number line represents the variable x, okay? So, a variable is something that can change value over time, right? So this action that we're doing, we're taking this point and we're sliding it towards A without ever it touching A. We call that x goes to, with this arrow, A minus. Why the minus sign at the end? Because it's always going to be smaller than A, right? We're approaching, we call it the left-hand limit, so I'll write that down. Left-hand limit. Okay. So we're approaching A from the left-hand side. That means that we're always going to be smaller than A, but we're never going to touch A. Okay? Okay, so if we're going to do this from the left-hand side, what are we going to do as well? We're going to do it from the right-hand side, right? So I'm going to pick this point here, and I'm going to slide it towards the left. I'm going to slide it towards A. It's going to be very close to A, but it does not actually equal A. So this action, we call it x goes to A plus. Okay? So this, we call this the right-hand limit. Okay, so x goes to A minus, I slide it over from the left-hand side. X goes to A plus, I slide it over from the right-hand side. And these two actions together we call it x goes to A without the minus and plus at the end. So if I say x goes to A, that means I'm thinking of these two situations at the same time, And it's kind of weird, right? But I'll explain some more later. So this means x goes to a. And then this is what we call, when we take a limit, this is what we're imagining, okay? But the picture isn't complete just yet. We did it on the number line, right? So now let's add one more dimension to it, right? This is one dimensional. But what we want to do is we want to analyze functions, and almost all of the functions that we're going to see in high school, you know, is going to be on 2D, right? So let's add another axis to it. We have the coordinate plane with the x and y axis, okay? So this is the x-axis, the y-axis. And what I'm going to do is I'm just going to draw a random function like that. Okay, what I'm going to do is I'm going to do the same thing. I'm going to pick a point, A. And then, since this is a function, it's function value. Let's call this function value L, okay? I'm going to do the same thing here, okay? So I'm going to look at the x-axis, and remember, right? We're getting closer to A without ever touching A. Do you guys get that concept? So, for example, if A equals 2, what are we doing here? If A equals 2, if we approach it from the right-hand side, we're going from 2.1, and then 2.01, and then 2.000, whatever, 1. We're getting smaller and smaller, but we're never touching 2. You guys get that? Okay, yeah. And then from the other side, we go 1.9, 1.99, and then you can add whatever many 9s that you want, but we're never going to touch the actual thing that we're going to. So we're going to do that same thing here. We're going to get closer to A. Let's start with the left-hand side, okay? But since we added another dimension, let's call this function f of x, we're going to watch how the function behaves as we go to the left-hand side of A, right? We're going to observe the y value as x approaches A, okay? So I go from here and I approach A like that. So this would be the most important diagram for today, I think. And then imagine a point on the function, right? Since we're in 2 dimensions now, this point, as its x-coordinate approaches A from the left-hand side, its y-coordinate sort of, okay, let's emphasize this a little bit. Let's draw it like that. Okay, as the x-coordinate goes to A, its y-coordinate goes up, and then as we get closer and closer and closer to A, what does the y value approach? It approaches L, right? So as x goes to A, y goes to L, but from what side? Is it always bigger than L, or is it smaller than L? Right? If I go here, then that means that the point on the function is going like that. Is it approaching from this way or that way? From the top down, right? So it's always going to be slightly bigger than L. So let's draw a little something like that. As the point approaches A. Now, same thing from the right-hand side. We're going to adjust our x-coordinate so that we always go closer to A from the right-hand side without it ever being A. And what happens? The point moves up like that, right? And then the y-coordinate also gets closer to L without it ever touching L. Do you get this picture, right? We're sliding this point around. We're getting closer to something without ever touching it, and we're observing how the function changes as the x-coordinate does that. And this action right here is what defines a true limit. So the limit, we call it like this. So LIM is the symbol that you're going to write. And then under the limit symbol, we're going to say x goes to A. Goes to A, right? The same thing that we wrote over here. And then whatever function we have, we're going to write after it. So f of x. And then that equals to L, okay? So this is our official way of writing down limits. So the limit of f of x as x goes to A is L. Okay, got that? Yeah. So remember, when we say x goes to a, we're doing two things at once, right? We're observing this from the left-hand side as we approach from the left-hand side, and we're also approaching from the right-hand side and observing that as well. If I say x goes to a, we have to do that all at once. Now, functions, do you guys remember what a function is? What defines a function? How do you know if something is a function or not?
Like if it crosses like if you put like a pencil, it crosses like 2 points.
Yeah, so that would be like the vertical line test, as you call it, right? But mathematically, what gives you the exact definition of a function? A function maps a domain to a range, right? We're going to talk about like sets, probably in continuity. We'll talk a little bit more about that. But it maps a group of numbers, whether that's the set of all real numbers or some very specific numbers, and it maps a set to another set, right? For most functions that we've encountered, including like linear and quadratic functions, these two sets are basically the set of all real numbers to the set of all real numbers. But in order for that relationship to be a function, you have to have a couple of things. For every element in the domain, right? This is just a side note, okay? So you don't have to write it if you don't want to. In the domain, it has to map to one and only one element in the range. Okay. I'm using the word range kind of loosely here. So x and y, so x is the domain, right? So y is actually not the range, it's something called the codomain, okay? Something called a codomain, and the points that you actually hit with the codomain is called the range. I'll talk about that more when we talk about sets and that kind of stuff. But the point is that functions, as long as there is one and only one corresponding element to every element in the domain, this becomes the function. In other words, functions don't have to be as smooth and pretty as the beautiful curve that I sketched here, right? So let's talk about some not so pretty functions. Have you heard of piecewise functions before? Okay, so piecewise functions are functions that are defined differently based on intervals of x. So I have to, let's do y equals x squared again. Let's have that. But instead of drawing the full parabola, I'm going to cut it short, and I'm going to add the condition in parentheses that x is only greater or equal to 0. And that changes things, right? That means I restricted the domain of this particular graph to be at 0 and onwards only. And then for elements less than 0, I can say, hey, y equals, I'm going to divide this, and then I'm going to say, I don't know, x minus 2 for every element less than 0. So this is what you would normally call a piecewise function, because it's divided into pieces. Okay, so there's a couple of important rules when we're dealing with piecewise functions. You have to look at the boundaries very, very carefully, okay? So if you're analyzing a piecewise function and it does something interesting, it's most likely that it does something interesting around the boundary, because that's where the function changes, right? That's where the equation of the function changes. So for this function, you see, what's f of 0, guys? If it's defined like this, what is f of 0? Do I plug 0 here or here? you see the restriction, x is less than 0, and x is greater or equal to the 0, right? So I have to plug it into the bottom one. So the function value is 0. So that means at 0, this is the actual value that the function has. We represent that by drawing a big closed hole, okay? Closed circle. And then x minus 2 for every element below that. So x minus 2, it's the slope of 1 and intercept of -2. So if this is the origin point, and I have -2 here, what I'm going to do is I'm going to draw a open circle, okay? I sort of exaggerated the size here, but I'm going to draw an open circle indicating that the function isn't actually defined here, right guys? F of 0 equals 0, so there's nothing at -2. But for anything slightly less than 0, it's immediately going to jump over to this line, right? So this is how we notate piecewise functions, and depending, on what equations you come up, they can get pretty complicated, but here's how you read them, right? You have to understand that throughout the course, you're going to see some complicated stuff, but I always want you to remember that even though the situation looks complicated, you can analyze it with the very basic principles that you learned here, okay? And you're going to see a lot of examples of that in your workbook and also in the quizzes as well. So, let's take a closer look at this. Okay, so I said that limit x goes to a f of x equals L. Well, let's take a look at what's happening over here. A note on the limit symbol, guys. For me, I write it like this, just a squiggly L. Some people, I've seen a lot of different styles. Some people like do this, x goes to a. Some people do whatever this is, x goes to a. So choose whatever format or style that you like. Some people just do this, whatever, okay? So let's study this function a little bit more. I'm going to take the limit as x goes to 0 plus of f of x. Okay, remember, going to 0 plus means we only look at the what side? Right-hand side, yeah? So if we only look at the right-hand side, what's going on? What does the y value approach as we approach 0 from the right-hand side? 0, right? I can observe as I slide it. You can slide your pencil or finger along the curve. It goes to 0, so that equals 0. But what's a little bit more interesting is what happens when x goes to 0 minus. 0 minus means, right, we approach it from the left-hand side. So what does the y value go to as we approach it from the left-hand side? Yeah, -2. Okay, then how about this? What is the limit x goes to 0 of f of x without the plus or minus? It's kind of confusing, right? We say it does not exist. Here's why. Okay, so have we got the stem?
I'll check right now.
Oh yeah. You know what? I'll do this. You can slide this. That. And then you can slide it like that. Hey! That was a bit little. Didn't happen today. Okay, so let me just get the camera angle here. Should I hire a camera director? Okay. So it's kind of confusing, right? The left-hand limit is the right-hand limit is 0, but the left-hand limit is -2, and there's this sort of like mismatch going on. So I'm going to teach you exactly how to identify the conditions for a limit to exist. This is very important, okay? There's 3 things you need to remember, just 3. All of these 3 things must be satisfied in order for the limit to exist, okay? Number 1, the left-hand limit exists. Okay, I'm going to write it in English for now, and then let's deal with symbols. The left-hand limit exists. Number 2, the right-hand limit exists. Number 3, the most important part, the left-hand limit has to equal the right-hand limit. If all of these 3 things are satisfied, then we can say that the limit exists. But even if one of these things are not found to be true, then the limit does not exist, and we denote it as D and E, okay? Does not exist. So let's take a look at a couple of scenarios here. Let's say that I have a function that goes like that, and then at this x coordinate, it jumps. Like that. How's that? So let's say that this is x equals a, and this value is alpha, and this value is beta, okay? Okay, so question, does the limit exist at x equals a? How would you answer that? We gotta look at 3 things, right? The left-hand limit, the right-hand limit, and if they equal each other. What's going on here? The left-hand limit is what? We approach it from the left-hand side. So what's the limit, guys? Alpha, right? We call alpha, beta. They're Greek letters. Alpha, beta, gamma, delta, yeah, you'll see those a lot. Okay, so number 1, let's write it in our limit notation. Limit of x goes to, is this a plus or a minus? A minus of f of x equals alpha. Okay, that exists, right? Number 2, limit x goes to a plus. What's that? We approach it from the right-hand side, right? That's what? Beta, right? The limit is beta. Okay, number 3, does alpha equal beta in this picture? It does not equal each other. What does that mean? That means that the limit does not exist. Okay? How about this? You might see a function where, I don't know, I can choose whatever I want with the function, right? As long as there's one element that's mapping to it. So what if I just draw a regular curve, but in the middle, I left this out, right? It's an open circle. What does an open circle mean, guys? It's not defined here. And I define it somewhere else. So again, let's call this top value alpha and beta, and let's call this A. Guys, does the limit exist? Right? Okay, so if you see, does the limit exist, what should you go through? You should go through these 3 things, right? Okay, so what's the left-hand limit? Beta. What's the right-hand limit? Beta. Remember that this is important, guys, right? So you're getting closer and closer to A, but you don't actually touch A. That means you're never going to suddenly go up here, right? That's only when you read the function value. You can say that f of A equals alpha, right? But the limit of f of x as x goes to A, because we've considered both sides, right? That is a different number. That's beta. That means it does exist. Okay? Okay, have you guys seen the graph of y equals 1 over x? Have we seen that? Okay, can we imagine what it looks like? Right, this is going to be a very important skill, right? We're going to do a lot of graph analysis, a lot of visual reasoning here. Some of the things that we do, I don't think you can find like anywhere in the curriculum or the IB curriculum, okay? So we're going to develop a very strong sense of visual reasoning that will be very helpful to us. Okay. If you plug in 1, this is 1. If you plug in 2, it's a half. If you plug in 3, it's 1/3, right? What do you notice as x gets bigger and bigger? The fraction gets smaller and smaller, right? Eventually, if we keep plugging big enough numbers, it's going to get close to 0. But will it ever reach 0? No. So that means, what if x got smaller? What if x was a very, very tiny number? Then this fraction would blow up, right? It will become very, very large. And then we're going to talk about infinity very soon. But does it ever cross the y? Does it have a y-intercept? Will it ever touch the y-axis? No. It's like that. This is called an asymptote if you haven't heard of it. Asymptotes are defined as lines where the graph gets closer and closer to, but never actually touch. And you're going to learn this in pre-calc 12 about like linear and linear rational functions and quadratic linear rational functions. Asymptotes is going to be a big part of analyzing it. Similar thing, if we plug in negative numbers, if I plug in -1, it will land at -1, right? And then if I plug in a very large negative number, then it will get close to 0, but will it ever actually be positive? No, that means that you'll get a symmetric image right here and then, okay? We're also going to talk a lot about symmetry, guys. You know parabolas, they're symmetric about their axis, right? This one, it's a point symmetry. This one is symmetric about its about the origin point. So what does point symmetry mean? If I draw a line from one of these points through the origin point, so that's the point of symmetry, and then it lands here, that means that this will always be equally distant to each other, okay? So that's a side note. So if we look at what's going on at x equals 0, it goes something like that, and it goes something like that. Does the limit exist, guys? Does the limit exist? Why do you think so? Left-hand limit exists, right-hand limit exists. Left-hand limit equals right-hand limit. Did you run through that in your head? It's kind of confusing, right? So let's step back for a bit and let's talk about infinity. Because what we've covered over there, I'm turning the angle a lot, but what we've covered over there is x going to a certain what? A certain fixed number on the number line. Is infinity on the number line? You don't think so, right? Infinity is not just a number that you can pluck somewhere on the number line. So I'm going to erase this piecewise function example, and then let's talk about infinity, because that's one of the new concepts that we get introduced to in calculus, and it's very important as well. When we're talking about functions like y equals 1 over x, it's a very good idea to have an understanding of what infinity looks like, because we have an asymptote and we have things going very big and things going very small. So what does infinity mean? Well, if I say x goes to infinity, what do you think that means? Yeah, so I'm going to do the same example on the number line first, right? If we have the number line, and I say x goes to infinity, I'm going to start with a point anywhere on the number line. And what I'm going to do is I'm going to move this point to the right, but we're not going towards a certain number. We're pulling it to the right forever. So infinity is not a number, as you guys said, on the number line, but it's kind of like a state of something getting larger without stopping, okay? Does that make sense? So this is x goes to infinity. And if I pull this point towards the left without stopping, what do you think that gets you to? Negative infinity. So x goes to negative infinity. So when we're talking about infinity, it's important to slightly modify these rules, because there isn't, a left and right limit, right? As long as your function goes, your y value of the function, as long as it goes to a certain value and gets closer to it, then you can say that the limit exists. This is called convergence, okay? So I need to draw two different graphs, and then you can tell me which one does the limit to infinity exist. This guy and this guy. Okay, which function would, as x goes to infinity, does the limit exist? for this one? What do you think? If I call this like, I don't know, alpha? So x goes to infinity means what? We slide the point towards the right forever, right? So as we slide this point further and further to the right, the function gets closer and closer to what? Alpha, right? Without ever touching it, right? So we can say that the limit of this function as x goes to infinity equals alpha. So we just need to look at that side. But for this one, right, you're going to learn exponential functions, like things getting bigger and bigger as you go. But if you slide across to the right, going to infinity, will you ever reach a real numbered value? No. But we have a special notation for this, okay? We can say that as x goes to infinity, f of x goes to infinity. Okay, the limit exists for this one. Although we write down infinity, the limit does not exist for this one. Okay, then why do we write infinity? To show that it's going, it's increasing without stopping. Okay, so limit exists. This this phrase, we also have another name for that, and that name is convergence. So the function converges as x goes to infinity. But this function does not, right? Convergence means that the limit exists. Divergence is the opposite word. Divergence means not converging. Okay? Convergence and divergence has a lot of like applications in other contexts. You can apply this to like functions and limits, also in sequences and series. Does like a series converge or not? Does a sequence converge or not? Okay, so back to our examples. Okay. So now that we have a better understanding of things going to infinity and what infinity is, we can sort of apply the rules here to this particular function. As x goes to a minus, let's say. Let's look at that first. What does the function go to? Infinity, right? Does the limit exist? No, but we call it infinity because it's continuously rising and going towards that asymptote, right? And then limit x goes to a plus of f of x is going to be negative infinity. Now, it does not, obviously, this does not adhere to any of these rules, so the limit does not exist, right? But we should be able to notate these kinds of things. Okay, so the limit does not exist for that one. The limit does exist for this one. And the final one that I want to sort of briefly introduce to you is this. Okay, a function that looks like this, and it goes on forever. You know, like if you studied waves in physics, you know, Pre-Calc 12, you'll learn that as trig functions, but imagine just like a wave that goes on forever with the x-axis, right? Let's say that it oscillates between the y values of 0 and 1, okay? What would you say that, does x goes to infinity, does the limit of this function exist as x goes to infinity? What do you think? Probably not, right? Here's how you can tell. We keep going back and forth between 0 and 1, but in order for the limit to exist at infinity, the function has to go towards a very specific value. It has to approach it either from the bottom side or the top side, and it has to approach that value as we keep getting bigger and bigger. But as we go to infinity for this one, there's no sign of it like approaching to a certain value. We call that converging to a certain value. So this does not exist. We call this thing oscillating because it oscillates between two numbers. Okay, so do we get some understanding about whether that we can check if a limit exists or not in a function? Right? That's pretty cool. Yeah. So we've covered limits going to a certain number and limits going to infinity and negative infinity. So we've done like a very visual approach, which is very nice. Obviously, in calculus, there's like a perfect mix of like visual, like geometry, sort of analyzing, and then analyzing with algebra and equations. So let's take a little bit of a look at that. Okay. We've covered the geometric side, so now let's take a look at the algebraic side. So I'm going to erase. Can I erase this board? Yeah. Okay, so far we've learned limits. We've learned what functions are piecewise functions that are defined, and how to read piecewise functions, right? A closed circle means the function exists there. An open circle means the function does not exist there. And we've also learned that while the function value might be over here, the limit might be actually down here, depending on the function. Okay. Very nice. Now for the algebra part. Let's start with something easy, right? So here we just said f of x could be anything, any function about x. But now we're going to get more specific with algebra. Let's start with limit x goes to 5 of x squared minus 4. Okay? So what is going on here? We sort of have to keep that running in the back of our minds. Remember, x going to 5 means that we have to consider two things at once, right? We have to consider x going to 5 minus and then x going to 5 plus. For this one though, right, x squared minus 4, if you visualize that function, it's just a parabola. It's very smooth, there's no jumps, it's not piecewise, it's not anything weird like that. That means that we can simply plug in 5 into this limit, right? Because as it approaches 5, it approaches that function value. As long as the graph is not doing anything bizarre at that function value, we can just plug in 5 and get our limit value. So what's 5 squared? 25 minus 4 equals 21, right? Very simple enough. So when we're writing functions with multiple terms, it's always a good idea to put brackets around it after the limit sign to indicate that this is the function that we're dealing with in this limit, okay? Okay, that's pretty good and all. So here's some properties of limits that we need to remember. So algebraic properties. Okay, number one, you can add and subtract limits. So if I have two different expressions or two different functions, then limit of x goes to a of f of x plus minus g of x. Do we know what the plus minus means, right? Yeah. I'm a person that uses curly brackets outside of like the regular brackets. So some people don't use curly brackets in algebra, but that's my style. This, we can split the limit, right? If something goes to a certain number and something else goes to a certain number, you can split it. Limit x goes to a of f of x plus minus limit x goes to a of g of x. Of course, this is assuming that none of them like go to infinity or oscillate or does any of that weird stuff. We're assuming that the limits of both of these exist, and if they both exist, then we can split the limit into addition. The next thing is constant multiplication. So limit x goes to a of, let's say I have a constant c multiplied by f of x, then I can pull out the constant outside the limit. Right? That's intuitive, right? Yeah. C times limit x goes to a of f of x. What I can also do is I can multiply and divide them, but we have to be sort of careful about when we're doing these things. Okay, limit x goes to a f of x times g of x. We can split that limit into 2 and then multiply those together. Limit x goes to a of g of x. This is, I think this is all written in your notes, right? Yeah. And this is assuming that they both exist, right? And then finally, division can happen as long as the denominator does not go to 0. Okay, because if the denominator goes to 0, things get very complicated very fast. But if they both exist as nice non-zero real numbers, then we can totally split the limits. So these are basically the algebraic properties that you can use when you're evaluating, some more complicated types of limits. Okay, it's very nice and all, but here comes the real challenge. This is where things start to get interesting. Can I erase this? Because it's in the notes. Yeah. So these are very easy, right? Just plug them in and you're done with it, right? But obviously that's not going to be, I don't think it's going to be much frequently tested if you're sitting for a calculus exam. Okay, look at this limit. Let's do limit x goes to 1. I'm going to do a fraction. Okay, guys. Let's take a look at that. Okay, so this one, limit x goes to 1 of x squared plus 2x minus 3 over x minus 1. Okay, the first instinct might be to plug in, and that's actually a very good thing, okay? I'm going to emphasize this a lot. The fundamental action that you should be doing when you first see a limit is to plug in. Plug in first. If you get a very nice number, then yeah, you're done with it. But look at this fraction. If I plug in x equals 1, what happens to the denominator? 0. What happens to the numerator? Plug in 1. 0. What answer do you get? Is this 0 over 0?
No, it's no solution.
Right, because we've learned that if a denominator is going to equal 0, then that number is not defined. So does the limit not exist? But the numerator is also 0, right? It's kind of a weird situation that we have here, right? This is called what we call an indeterminate form. An indeterminate form means that you can't get the answer right away just by plugging in and looking at it. So in calculus, there's 7 types of indeterminate forms. If you get one of these forms when you plug in a number, that means that you have to do some extra steps to get to the final answer. These 7 forms are, we just discovered 0 over 0. There's infinity over infinity, infinity minus infinity, 0 times infinity, what's it? Infinity to the power of 0, 1 to the power of infinity, and 0 to the power of 0. So if you get any of these weird looking expressions when you're trying to calculate a limit, that means that it's indeterminate and you can't get the answer right away. Okay, so I guess that's good and all, but how would you actually get to the answer, right? So for this particular expression, we're dealing with the 0 over 0 limit, and I think we'll mostly be dealing with the first 4 or the first 3 in this course. In the full calculus course, you would get to know some of these limits as well, but I don't think that's going to be part of our scope. So let's focus on, mainly we're going to focus on these two. Infinity minus infinity is sort of similar to what we're going to do with these two forms. Okay, so that's indeterminate forms for now. What we can do here is look at that quadratic expression at the top. What can you do with it? Can you do anything with this expression at the top? You can simplify it. Specifically, you can factor it, right? Well, how can you factor this? How did you learn to factor trinomials, by the way? Because there's a lot of methods, and a lot of them are not very fast. Yeah. Okay, did you learn it this way? 1, 1, 3 minus 1, bum, bum. Yeah? Yeah, the cross multiplying and adding. Yeah, that's the most efficient way, I think. So you factor this, and remember, guys, when we're writing stuff out, we want to be, when the teacher says, like, show your work, we want to be very formal about this, so we keep writing the limit symbol, okay? Don't forget the limit symbol. Limit x goes to 1, and let's factor this. X plus 3, and then we have what? X minus 1 over x minus 1. Okay, guys, now this is the time to think about this, okay? It's very important. What do you want to do right now with this? What do you want to do? Cross it out, right? Cross it out. But you should always be very, very careful when you cross things out in math. Okay? For example, the equation, solve the quadratic equation, x squared equals 4x. Okay, I'm going to cross this out, so x equals 4. Is that the full solution? No. Why not? What's the other solution? X squared equals 4x. What's the other solution? X equals 0, right? Plug in 0, both sides go to 0. But why did I only get x equals 4? Because I crossed it out. When you're crossing it out, what does crossing out mean? You divide both sides of the equation by the same thing, right? Can you divide by 0? No, you can't, right? So when you're crossing things out, it's always important to check if the thing that you're crossing out is not equal to 0. Because if it is, you're not allowed to cross it out. Yeah? Look at this limit. X is going to 1. Can I cross this out? Why? What does x goes to 1 mean back here?
It doesn't go like that.
Yeah, it goes close to 1, but does it actually ever equal 1? No, it doesn't. That's why we can cross this out. If this was literally 1 minus 1 over 1 plus 2 minus 3, would this have an answer? No, this would be undefined. But this is a limit, it's different. We're getting close to 1, but we're not actually equaling 1, so that's why we're allowed to cross it out. I don't think the majority of people who's doing limits understands why they're doing this, but it's very important, especially when you get to those very hard problems. It's important to go back to first principles and think about what is actually going on. Okay, so that means that now we can plug in 1 and then we get an answer, right? 4. So it's not very apparent at first, right? It's 0 over 0, but through factoring, we can get to a pretty nice answer. Okay, what time is it? 4:01. Should we start on the workbook? Do you think it's a good time to start the workbook? Yeah. There's some other forms, but we might cover them next time. Wait. Yeah, I think we have a lot of material to go there as well. Guys, can we turn to number 13? Number 13. Okay, we're starting at number 13 because it's kind of like a continuation of this, okay? So workbook number 13. Okay, guys, chapter 1, this is chapter 1, number 13. What does it say? Evaluate that plus that. Okay, the first one, we've just seen it, right? Can we all solve the first one? Limit x goes to 1, x squared plus x minus 2 over x squared minus x. Okay, what do you do when you first see a limit? Hint, hint. Plug it in. Okay, what happens if you plug it in? Do you get a nice number or do you get an indeterminate form? You get an indeterminate form. That means we gotta modify the expression. One of the things that we're going to do super a lot is getting comfortable with modifying different expressions so that we can get the information that we want. Okay? So, what do you want to do? It's a polynomial, so we can factor it. What happens if you factor the denominator? X times x minus 1. What happens if you factor the numerator? X
minus 2, x plus 1.
Really?
Oh wait, oh
Guys?
it's plus 2 and minus 1.
Yeah. Okay. Right? So what can we do? We can, knowing that this expression x minus 1 can never equal 0, right? We can cross it out and then plug in 1 to get 1 over 2, so that's 2. Do you understand this process? Yeah, okay. Okay, now look at the second one. Oh my gosh, we have a square root. Okay, first thing that you do, you plug it in. What happens when you plug it in? Go ahead and plug it in. What happens if you plug it in, the second one? Guys, are we having trouble plugging in numbers? I hope not. What does the numerator go to when x goes to negative 3? Goes to 0, right? How about the denominator? What's negative 3 plus 4? 1. Square root of 1 minus 1 is 0. So it says 0 over 0, indeterminate. Okay. Why is it 0 over 0? We kind of found out during our factoring, but why is it 0 over 0? What's annoying us? It's these factors, right? There's a factor in both the numerator and the denominator that makes this fraction go to 0, and we want to get rid of that as quickly as possible, but now there's like a square root thing going on, right? What do you think might be a strategy that will help us uncover the factor that's making the whole thing go to 0? Guys, do math teachers like it when you put your answer like this?
No.
No, what do you do here?
We put square.
You rationalize, right? You multiply
Yeah.
both sides to rationalize, okay? What happens if you want to rationalize something like that? Remember in your radicals class? You multiply the conjugate, right? With the sign opposite. Why do you multiply by the conjugate on both the numerator and the denominator? Because a minus b, a plus b, what's that? A squared minus b squared, right? If you want to get rid of the square root, you have to square that thing. But the easiest way to do that is to multiply the conjugate and use the difference of squares law, right? So we're going to apply that exact same principle here. So you should keep this in your head, is that if I have a 0 over 0 indeterminate form, and there's like radicals and roots involved, I should think about rationalizing whatever it could be the numerator or the denominator, but I have to rationalize whatever part the square root the radicals are in. So what am I going to multiply? X plus 4 plus 1, right?
Yeah.
Switch the signs, and then I have to do that to both the denominator and the numerator. Like that. Okay, so what happens here? A squared minus b squared. What's square root of x plus 4 squared? It's x plus 4, right? So we get x plus 4, and then minus 1 squared, limit x goes to -3. And then what do we have on the numerator? Do not expand the numerator just yet, okay? We have to observe the expression first. Yeah, another good habit to do, guys. Don't embark yourself on a journey of messy calculations until you figured everything out. Because often, many times, the problem will set up the equations and set up the numbers so that a simpler way of calculating things are possible. It's just you have to notice that. Right, so do we end up on this expression, guys? Yeah. What's x plus 4 minus 1? What's this? No, algebraically, if I simplify this, what's it going to be? X plus 3. What do you notice? Oh my gosh, the same things in the numerator. So you can cancel them out, plug in -3, and you get what? Square root of 1 plus 1, which is 2. Okay? So the answer is you add 2 and 2, you get 4 for number 13. Okay, guys? Okay, so now let's go back to the beginning. Do you guys know the difference of cubes formula? Difference of cubes?
I don't know about memory, but
Yeah. Okay, so let me tell you a very easy way to memorize that, okay? Difference of cubes. That's going to show up a lot in, algebra, calculus, whatever. Okay, a cubed plus b cubed. A cubed minus b cubed. Okay? What we're going to do is, first, we're going to ignore the cubes and just write a plus b here. Guys, watch. A plus b. Okay? And then what we're going to do is we're going to square a and square b and then add them both. And then in the middle, we're going to multiply these and flip the sign. So if this is plus, right? There's a plus here. We want to do a minus here. A, B. Okay? And that's how you factor cubes, right? It's very easy to memorize, right? So this one, we go what? A minus B. And then we do the same thing. We add a cubed and a squared and b squared, sorry. And then it's a minus sign, right? So what do? We put a plus sign and then do a, b. So quick question, limit x goes to 2, x minus 2, x cubed minus 8. Let's do this. Right, you plug in it's a 0 over 0 indeterminate. You gotta modify the expression somehow, right? How would you factor this? So we leave x minus 2 because that's already there. We go what? 8 is what? 2 cubed, right? So we go x minus 2. We do x squared, and then we do 2x, but it's a plus, right? Plus 2x. Plus 2 squared is what? 4. And then we can cross this out and then plug it into 4 plus 4 plus 4 equals what? 12, right? Yeah, so you should be familiar with cube and cube roots. Some annoying teachers might put a cube root on your limit, right? Let's just say oh my gosh, there's a cube root in my denominator. Like that, something like that. then you gotta utilize what? You gotta utilize this, right? You gotta multiply. If this is like a minus b, you gotta multiply what? Cube root of a squared, so that's what, like a to the power of 2 over 3, plus like there, multiply these two, and then plus like b squared, like, yeah, like that, okay? I don't think I put any of the cube roots in my questions, but that's what some teachers do, okay? Okay, so we've done some algebra now, and hopefully you're comfortable with how to approach it and how to solve it. So let's go back to number 1. I think number 1 you can do on your own, right? Can you do number 1 on your own? Yeah. Okay. Okay, guys, wait. So I'm going to erase this, and then we'll go full workbook mode. Okay. Should we do number 2? Would that be nice?
Yeah.
Okay, we got focus. Good. Number 2. So this is chapter 1.1, number 2. If f of x is like that, what is the value of k? So what do we got here, guys? What do we call these types of functions? What do we call these functions? Remember, it's defined differently based on the interval of x. We call it piecewise, right? Piecewise? Right, so what's going on here, guys? The limit goes to 3 exists. And we have to find our unknown k, right? So what does the limit exist mean? The left-hand limit and the right-hand limit has to exist, and they have to equal each other, right? But what's the right-hand limit here? The right-hand side is what? This side, right? We're going slightly larger than 3. The left-hand limit will be on the bottom function, right? So what we can do is we can plug in 3 into the top one, right? That means this function as x approaches 3, so that's 9 plus 3 minus k, yeah, equals, what's, if you plug in 3 here, it's negative 6 plus k. Yeah, so what do? You solve for k, 12 plus 6, k equals 9, is it? Yeah, k equals 9. Oh my, wow, we solved it. That's it, right? Okay. Number 3 you can do on your own. Remember, especially for problems like number 3, you have to remember the 3 conditions for the limit to exist. What were they, guys? The 3 conditions for a limit to exist. Right-hand limit exists. Left-hand limit exists. Left-hand and right-hand has to equal to each other. Good. Let's move on. Let's take a look at number 5. Number 5. Okay, absolute values, guys. Do we know how to deal with absolute values? Absolute values, especially like in some of the toughest problems, are like dealing with absolute values within functions. So let's get this straight before we move on. If I have something inside an absolute value, how do I take the absolute value out? I need to know something. Because we can't directly deal with absolute values without knowing a key piece of information here. you have to know if the sign of the thing inside is going to be plus or minus. So you have to know if the thing inside is going to be positive or negative. 0, it doesn't matter because, it goes to 0 on both sides. But if the thing inside is negative, we have to put a negative sign to whatever expression is inside, right? We say that an absolute value of -4 is 4, right? But what's actually happening here? We slap another negative sign in front of the -4 to make it 4, right? That's what's algebraically happening. Okay, knowing that, let's take a look at this limit. Limit x goes to 3 plus 2x minus 6 over x minus 3. What do we want to do? We want to plug it in. It goes to what? 0 over 0. So we want to factor it, but there's an absolute sign standing in our way. So what do? We have to determine if that expression inside 2x minus 6 is going to be positive or negative. X goes to 3 plus. Is this going to be positive or negative? What does 3 plus mean? It's slightly bigger, it's slightly larger than 3. Okay, so 2 times 3 is 6, but 2 times something slightly larger than 3 is going to be something slightly larger than 6. So something slightly larger than 6 minus 6 is what? Positive. That means we can get rid of it, and then we don't have to do any sign changes. And then this is very easy to factor, right? The x minus 3 factors away, leaving you with what? 2. How about the next one? Limit x goes to 3 minus this time of x minus 3 absolute value over x minus 3. So if for signs, we might want to underline it and indicate that it's positive. It's always a good habit to keep track of your signs. This expression, x minus 3, is this going to be positive or negative as x goes to 3 minus? It's going to be negative because it's going to be slightly smaller than 3. So there we go, it's negative. That means we have to put a negative sign in front of it as the limit goes to 3 minus. This one factors out, so that leaves us with -1. Do we get that? So the final answer is 1. Yeah, okay. Okay, number 6, you can try on your own. Number 7, we have time. Okay. Let's go on to number 7 here. Here is where I'm going to introduce you to a very powerful. Okay. A very powerful tool that we'll use, maybe not as much in this course, but it's a tool that you will use all the time when you're calculating stuff in like a full calculus course. The graph of y equals f of x is shown. Let's quickly draw that. We have -2, -1, 1. And we have that curve going down, and then we have that curve going like that. And then we have open hole, and then connect those two, and then like that. So that's 2, 1, 0, and you get it, right? Evaluate limit x goes to -1 of f of x plus the limit x goes to 1 plus of f of x. No, not f of x, but f of x minus 1. This one we're very familiar with, right? So what's the answer here for the first one? X goes to -1. Left hand, you look at the left hand limit, you look at the right hand limit, where does it go to? 1, exactly. So this is 1, but this is sort of kind of new, right? We have a different thing inside of f of x. Now there's 2 ways to do it. You could just try to plug it in and try to figure out where it goes. if this is 1 plus it's slightly larger than 1, you subtract 1 from slightly larger than 1, and that goes to what? 0 plus, right? So 0 plus is what? The limit to 0 plus. Trace it from the right-hand side, right? From the right-hand side, because it's 0 plus, right? I'm going from here to here, like that. So that goes to 0, right? Yeah. So we can do it like that. Or if you're too confused about anything, especially when you're like solving a complicated equation, you might have heard of substitution before, right? It's a very simple substitution now, but I usually put my substituting variable as t, okay? If I say x minus 1 equals t, then as x goes to 1 plus, what does t go to? Goes to 0 plus, right? Then we can rewrite this limit as limit t goes to 0 plus of f of t, and it's much more simpler to look at, right? And then we can get to the same answer, and the answer is 1. Yeah, 1 plus 0 equals 1, like that, right? Okay, what's next? Ooh, number 8. Number 8. I'm debating on whether I should or should not do this today. Do you have the capacity to take in more mental information, or should we stop with the new content? Stop with it for now. So number 8, you might want to try to look at it. What's different about number 8 than what we've previously done?
We got 2f and 2f.
Yeah, so what do you call that? You might have not learned that. Well, if a function is inside another function, we call that composite functions, okay? Composite means that there's a function inside another function, and there could be another function inside of that. So like a 2 or 3 layered, multi-layered functions. And the concept that people struggle with the most, and sometimes is going to be the topic of some of the most difficult questions in calculus, is on the subject of composite functions. But that doesn't mean it's hard, just means that you have to know exactly what you're doing. So we'll cover composite functions the next time. So you could think about it, or you can leave it blank for now. Number 9, can you do this in your head? I think you can. Right? We just have to remember our algebraic properties of limits, right? Just plug it in, right? Everything's going to 2, right? So you can do 3 times 1 minus 2 times 2, right? You got how that works? Yeah, so it's following the algebraic properties, but it's, it's very intuitive, right? You sort of plug it in as long as it's not going to indeterminate. So that's -1. Okay. Okay, guys. Number 10. Let's do that together as well. 10. Okay. Here's where the concept of modifying comes in very handy. Evaluate 2x squared plus f of x, x squared minus f of x, but we're not given explicitly f of x, right? So what are we going to do? X goes to 0, 2x squared plus f of x, x squared minus f of x. But we're only given that as x goes to 0, f of x over x equals 5, right? So what are we going to do about this? We have to modify our expression so that we can use this fact, because in math, everything is given for a reason, except if you're solving the SAT where, you know, I took the SAT on Saturday. Like a couple of questions on there give you useless information to throw you off, but most math questions only give you the essential information, which means you have to use this somehow, right? What do we have? F of x over x. We know the limit for this expression only, but we don't have an over x in here, right? So what can we do? What can we do to modify this expression so that we can actually use this fact? Okay, right? Divide by x on both the numerator and denominator so the actual value doesn't change. So it becomes 2x plus f of x over x, x minus f of x over x. Right, guys? So whenever this comes in handy, I like to do a cross arrow over this and say, hey, this converges to 5, right? Remember, convergence means it goes to a real number. So this converges to 5, and then what happens to the 2x and x? I plug in x equals 0, this goes to 0, and this goes to 0, right guys? So we get 5 over 5, which is 1. Okay, do we understand, right? So I encourage you to do, number 11 is for homework. Remember, if you have something uncomfortable looking, maybe substitution is going to be the right way. Number 12, ooh. Number 12, here, I'll tell you the cheeky way to solve it. Like, it's technically a valid solution, but the formal way to solve it is kind of more nuanced. Number 12, limit x goes to infinity of f of x equals infinity, and limit f of x minus g of x goes to 1. What is f of x plus f of x, f of x plus g of x over f of x as x goes to infinity? Kind of makes you think, right? So the final thing that we're trying to do is x goes to infinity of f of x plus g of x over f of x. And you know what? I might simplify that to 1 plus f of x over g of x. Does that make sense? Like that, because this goes to 1, right? We can pull out anything that goes to 1, goes to a constant. So I need the ratio f of x over g of x. I know that f of x goes to infinity, and f of x minus g of x goes to 1, but I don't know the exact expression, right? So here's the quick way to solve it. You can make up your own f of x and g of x as long as all the conditions are met, right? Because you're trying to get to the answer and you're not trying to prove this for all possible functions. So what's a function? What's a very simple function that goes to infinity when x goes to infinity? X, right? Choose the simplest possible option. So if I say f of x equals x, then what could the expression of g of x be? The end result has to be a constant, so obviously you want to cancel out the x, right? So g of x should be negative x, but you want it to be 1, right? Remember, there's a negative sign at g, right? So it's f of x minus g of x, and that's 1. So I want x minus 1, right? Because it comes out negative sign as positive, so we get the 1. Yeah? Okay, so now we got our examples, our very simple examples for this. So f of x is x and g of x is negative x minus 1. And I realize that I haven't taught you how to do this yet. Okay, we'll do this next time, right? Okay. The trick here is to divide both sides by x, and then that goes to like 1 over negative 1 minus 1 over x. So this goes to 0, so it's negative 1. But, okay, sorry guys. Skip number 12 for now. I'll tell you like how to do it formally next time. We've done 13. You can do 14 as homework. And that's kind of where we end for today. So okay, so homework, guys, for Thursday is to obviously I'm not going to write it, but you have to review the notes that we did today, right? We went all the way up to this part, evaluating the 0 over 0 indeterminate form, okay? So review your notes and the diagrams that you drew, and then what you have to solve is the workbook for number 2, number 1, number 3. So this is chapter 1-1, number 1, number 3, number 4, number 6. So basically anything that we haven't solved today. Try number 8 as like a challenge, but you don't have to do it. Did we do number 9? We did number 9. We did number 10. I told you guys to do number 11 and number 12. You can skip. We did number 13, so 14. Okay, and that would be your homework for today. Do you guys have any last questions? We'll leave number 12 up for next time. No? Okay, so how was your first class? Right, we got started on limits, so this will be the foundation of everything next else that we will do in this course. So, yeah, it was a great first class, and I'll see you guys on Thursday, okay?
I'll be on Thursday. I can't make Thursdays.
Oh yeah, okay. Then you can watch the recordings, but make sure to review. Okay. All right, bye guys.
Thank you. Just got a notification you got an English quiz tomorrow.
Yes.
They didn't tell you? No, she told me like that.